set in stone, but you think of getting some people from industry to come and like give talks. So that could maybe happen at these meetings or at other times throughout the week. We might go out into like the city and like go to some firms and like just see like what the companies are working on. So that's like all from Gallagher. And then also I'm working to try to get us a tour of Draper Labs. They do like military contracting and work on a lot of like advanced systems. So that's something that's in the works. And then also like trying to get some other speakers. So like no, this isn't confirmed at all, but there's a chance we might get someone from OpenAI at some point. Nothing is set in stone on that, but if it does come to fruition, of course, I'll let you all know. And then also for eBoard, there are some open positions. So there's the director of marketing and then also like director of outreach. So if that interests you, please reach out to us. I know some people already have. The way that'll work is you'll get in touch with us. We'll give you the details of like what the position is, like what we're looking for. And then you're gonna come up with like how you would like run that position, some initiatives you might come up with. You'll come in front of the eBoard and just like explain that to us. We'll just have a conversation. And then based on that, as the Constitution says, the eBoard will choose whoever for each position. Is there anything else?
You wanna introduce eBoard?
Yeah, we're all gonna, so the current eBoard, yeah, we can introduce ourselves. So I'm Stephen Roach. I'm a senior and I'm studying computer science and math. And then my research interests are a little varied. So most recently, like last summer, I was working on pinpointing an aircraft's position, so latitude and longitude, using some machine learning methods and Earth's magnetic fields. I've also done some stuff with flood prediction and zebrafish brains. So yeah, pretty cool, I think.
My name is Jason. I'm giving this talk. I'm a CS Math senior doing research in Professor Donnelly's computer vision lab, working on mostly electron microscopy data sets and how to do image instant segmentation on 3D structures. I've also done like a little bit of work on CT scans and MRI scans. And if you're grab a chair, you should grab a chair for that. I also on like segmenting heart structures, rib structures, that kind of thing in biomedical data sets.
My name is Xander. I'm a sophomore studying CS and math. My research interests are in natural language processing, specifically planning domain problems on edge devices. Up to rock climbing.
Emma.
Yeah.
Oh, hi. I'm a junior. I'm a bio major with a math minor. I'm not CS, I'm sorry, but my research is in computational biology and working with really like single cell RNA data sets. For like pattern recognition and like association with the
Okay, I'll get started with the talk. If you have any questions at any point, raise your hand, interrupt.
Yes, and also if you have not signed in this on the sign up sheet, please do so afterward. And if you're not already in the Discord or have no way to contact us, also talk to us on your.
I've given this talk many times. I'm doing this on very short notice due to a certain eBoard member, so we'll see how it goes. So who here is can you raise your hand if you're a CS major? Hands down if you're a math major. Very nice, very nice. Who here has heard or like watched a lecture, read an article about ML? Very nice. How about any hands-on experience with PyTorch or TensorFlow? Very nice. Okay. Okay. If you are interested in the link to the slides, here's a URL. If you're interested in a reading list, a recommended reading list, here's a link to the URL. Slides will be also posted in the Discord server. Okay, so this is a very high level talk talking about various things in machine learning. And first of all, we're going to justify the multi-layer perceptron and like what theorems it satisfies, in particular the universal function approximation. We're going to talk about optimization methods in deep learning, supervised learning, unsupervised reinforcement learning. We're going to talk about inductive biases and how this justifies certain types of architectures we choose, and novel topics, new research areas in machine learning. If you're interested in pursuing this kind of thing in the future. So universal function approximation. Who here has heard about Taylor series or Fourier series? Okay, so we know what a Taylor series is. It's just an infinite polynomial. So you have sigma an xn. And you can choose your an to fit your particular data. If you have a set of points modeling, I don't know, heights of people depending on how much milk they drink. And then you put this in Excel and then you do curve fitting, what you get is a polynomial fitting to it. And with higher degree polynomials, the idea is that you can model more complex data. So yeah. So with polynomial degree 1, you can fit a straight line, any straight line in fact. With a polynomial of degree 2, you can fit a quadratic function, etc., etc. The point is, your parameters are your coefficients, and with more coefficients, you can represent more complex data. So that is what the Taylor series and the Fourier series is like, in general. But these types of functions are limited. It is not a universal function class. You cannot model, for example, a sinusoid well with an infinite amount of polynomials, with a finite number of polynomials. And if you try to fit, and with like more terms, you get higher precision. As you can see, this is a square wave. You can see. So MLPs are based on a different function class. They're based on, they're very inspired by linear algebra, which is linear equations, which can be seen through this equation Wx plus b, which is just the generalization of the equation W is equal to mx plus c or whatever, which is just a straight line. But in higher dimensions, you get a hyperplane, right? And what you do is you slap on a nonlinearity onto it to get a nonlinear function. Now, the usual function of choice is called the ReLU. It looks like this. This is x, this is y, and it goes straight and it goes up. And it's mathematically defined as the maximum between 0 and x. And magic things happen if you put a linear function here, ax plus b. If you've taken linear algebra or multivariable calculus, you'll notice that the A here just means it's a matrix, and the x here should be a vector. And so you're dealing with multiple coordinates and inputs and potentially outputs. And the idea is each one of these models a linear-ish function. And if you stack them, you can model functions of higher complexity, similar with how in this Taylor series, with more terms, you get more complex functions. With more layers in the multi-layer perceptron, or more more perceptrons in a single layer, you can model more complex functions. And the way to think about it is that they're modeling more semantically complex objects. So you might have heard, like in the explanations for CNNs, that the first layer might be like an edge detector, a corner detector. And like by the end, you might have a detector for like fluffy dog ears or something. So this is a blog article by DistillPub. I forgot who wrote it. It might have been Christopher Olah, but they use some fancy technique in order to extract the features, the exact type of features that each type of layer is trying to detect. So the first layer tries to detect edges, and then you get more complicated textures, patterns, body parts or animal parts, and then you get objects here. And then you can think of CNNs as basically doing template matching if you're familiar with traditional computer vision terminology. But there's a disclaimer here that you can actually make this show whatever you want. If you're interested in looking at the details, look at the slides later. But why is this nonlinearity important? This ReLU nonlinearity. Like, what does this thing do to this straight line? Because if you stack if you simply stack linear layers atop each other, by that I mean you have a layer that looks like this. And then you just do like another A plus B. These are different A's, these are different B's, so on and so forth. It's still a linear function class, and you know, if you've taken linear algebra, that the span is the same or whatever. The reason is that you have the universal function approximation theorem, which states that with two layers of a multi-layer perceptron, you can actually model with two layers, but with an infinite amount of perceptrons. So like infinite dimension in A, you can model any function class. And the reason you can do that is because with 2 or 3 neurons, you can model a spike function. And by composing these spike functions arbitrarily, you can model any function. By that, I mean, if a function looks like this, you can imagine adding a bunch of spikes like this. And with an infinite amount of them, you can reach an arbitrary amount of precision or accuracy or whatever metric you want to use. So that is why multi-layer perceptrons are more powerful than, like, say, Taylor series or whatnot. So next, we're going to go into optimization. If anyone has any questions.
You use the word perceptron. What does that mean?
A perceptron, very good question. So this is a multi-layer perceptron. This is a single layer, and this is a single perceptron, right? So what a perceptron does is this is a perceptron. It takes in multiple inputs, let's say x0, x1, x2, and it has a set of weights. And let's say W0, W1, W2. And it also has a bias. And what it outputs is the nonlinearity W0, x0 plus W1, x1 plus W2, x2 plus B plus. And this is the output of the function. And it forms a sort of dense connection between every possible input is connected to every single perceptron at the next layer, so on and so forth. Yes, any other questions? All right. So now that we have this functional class, what exactly is machine learning? Given a set of data you're trying to predict, what exactly do you do to adjust or like find these coefficients? So there are multiple paradigms. The most classic example is the MNIST example, where you're given a multi-layer perceptron, and as input, you're given the brightness values of a picture of a digit. So like if I have like 0, and this is white or black or something. So like this say is like pixel value 0, pixel value 0, and then once it hits something, it's like pixel value 1. Then this can be transformed into a vector, which completely represents this data. And you can feed it into your multi-layer perceptron. Okay. And what you do is you have a loss function which represents how wrong your model is, or which represents how wrong your model is. If you've taken statistics, you might have heard of like mean squared error, which is like, let's say you're doing stock predictions for some godforsaken reason. You do the loss function is equal to sigma y minus y hat squared, and then you can do an average or something, where y is like the true value of the stock, and like y is what your model predicts, and you do a squared function. And the reason we're doing the squared function is because we want a convex thing to optimize over, but we're not going to get into that. But basically, imagine you have this differentiable function, This is why you should take Calc 2. You have this differentiable function which tells you how wrong your model weights are, depending on your input data, which is your set of x's and y's. X's are like the inputs, and y's are what they should predict. A disclaimer: this is like part of supervised learning. I'll later go into like unsupervised learning and reinforcement learning to talk about how they learn without human annotations. These are just example loss functions, which people use in various cases for classification problems, like given this image, is this a 0, a 1, a 2, a 3, yada yada. And there's but you don't want this just to be 0 on the training data. If you wanted, you could create a naive method. You could like store all the possible images in your data set, and then when you're given a new one, you just like see which one does this input image correspond to. You can return the corresponding label. Now that would be a perfect example of overfitting, right? You're just memorizing your data, and you're not learning any important patterns over it. So in the case of curve fitting, you can see this through this analogy. This curve describes the general trend of the data better than this, because we expect that there might be like some human error or some data collection error involved in gathering these x's and y's. Any questions? All right. So again, we have differentiable losses. The first type of loss is the task loss, or like how wrong your model is at predicting certain things. So that would be like MSE in the case of regression problems. But we also have regularization losses to prevent cases of overfitting. So we can regularize the output. Yes, or we can also regularize the parameters. If you've taken, you might want to take math statistics where they talk about like ridge losses and like how that helps make your linear regressions more robust. And if you're interested in like advanced methods in machine learning, there's something called like sharpness aware minimization, which makes your gradient descent algorithm find the models that are least bad in its neighborhood, which are least worst case bad in their neighborhood. I can talk about this after if you want. And in general, so now that you have this loss function that you're trying to optimize over and a set of function classes, what you can do is gradient descent or iterative optimization. So as opposed to things like polynomial curve fitting, there aren't exactly closed form solutions. So, if you have 2 points, there is exactly one line that goes through both of them, and you can write a math equation. And you guys should have known how to do this in middle school. And with like 3, you can fit a polynomial of degree 2, and so on and so forth. But with the amount of data we're dealing with, like in the millions or billions, you can't do this in closed form. So you need to use approximate methods which improve over time. So in general, there are 3 types of methods or more. There's gradient descent, stochastic gradient descent, and gradient flow. I'm only going to go into gradient descent. So the basic idea is you're somewhere on this loss landscape. So the loss is how wrong your model is. And you're trying to take small directions and you're trying to take small steps in the direction that minimizes your loss. So if this is your loss function, and for some reason you're here, you want to take small steps here, then you end up here, then you go down until you stabilize in the basin. And how that is represented in the equation is by saying, make your new parameter equal to the old parameter, updated by some small factor multiplied by how steep the loss function is at your current location. This is the general intuition behind gradient descent and even other methods like Adam. Where's Adam? Like Adam, just modify the gradient in some way to make it more efficient. And this is a projection. Who here knows what a projection is? Okay, here is a 2D projection or a 3D projection of the loss function of a very complicated, I don't know, ResNet probably. So if you're interested in that kind of methodology, you can see this paper in the link to the slides later. So gradient descent generally depends on the IID assumption, or like that you can independently sample your data. That means like you've collected all of your data beforehand and you just sample one with uniform probability. When you break this assumption, you run into more advanced types of machine learning, like continual learning, which is the case where you're constantly being fed new data. Like for some godforsaken reason, you're trying to predict the stock market exchange, and you're fed new data each day about what the current results are. When you sample, you're not sampling IID because you need to update based on new data as opposed to like old data or something. And in reinforcement learning, your learning algorithm actually influences what kind of data you receive. I won't get into that. So again, in general, there are 3 types of machine learning methods: supervised learning, where you have a set X and Y, which give you tuples of like what your input data should look like, what your input data could look like, and what it should output given that input. And there's unsupervised learning, where you're given a set of input data and you're trying to learn some underlying structure behind this data. And there's reinforcement learning, where you're given a non-differentiable loss function and you're still trying to optimize over it. So like, as a fun exercise, imagine having an MLP and like hooking up the outputs to a Atari controller. Like, how do you perform backpropagation? You can't, at least not trivially. And if you're interested in like advanced problems in supervised learning, I do research in connectomics in Professor Donglai-Wei's lab. If you're interested in that kind of thing, Professor Yuan Yuan also works in computer vision. Professor Pudumo works in NLP. I'm missing a bunch, but you can ask us after this talk. And you can do more than like modeling functions over vectors. You can actually model function classes themselves by modeling the Fourier coefficients, if there are any.
Explain backpropagation.
Okay, what is backpropagation? Do you want to explain backpropagation?
Sure. Okay, so like we basically have been in the weeds like of the math. So the idea is like you have this data, you're trying to like fit some function to your data. So like when you get some new input, you just apply your like optimized function, and it gives you like a pretty good output, hopefully, right? And then like at the beginning we were talking about these parameters, and the idea is you can like tune them. So over time, like you just like are doing this like multiplication and addition. If you have like the right coefficients, like you get a good output eventually. So the big question is like, well, how is like your computer system like tuning these coefficients to basically like get the right ones? So the idea is you start out like you have no idea what the weights are at the beginning. And you just kind of just take random guesses. So if you had like, say you had a really simple function where you wanted like 3 of these, you just have like A1, A2, and A3, you might just pick like random numbers, like from say 0 to 1, so like 0.5, 0.8, or whatever. And then what backpropagation does is this big algorithm that says like, okay, we chose like these coefficients, we're gonna have input like a bunch of data, and we're gonna use our loss function to calculate like how inaccurate it is. You can imagine like you're gonna be pretty wrong. Like the answer is supposed to be like 10, you might get like 50 or some weird number. So then, as Jason was explaining, like if you have this like neural network where it's like you have your perceptrons all in this like layer together, and then you're passing in some like input data. You run all these calculations down the network. So you might have like a bunch of these layers that are all performing these calculations. Like you might be doing some matrix multiplication, you're adding a vector, and then you're applying this like rate function. And you do that down the whole network until you get some like value. Say 10. So then, without I guess going like too far into like the calculus and everything, you basically can see like, okay, how much did the weight here? So like if this came in with some like weight 1, which like we were talking about right here, you can see like how much does weight 1 like actually affect our output here. So the idea is like, okay, like if weight 1 has like a huge effect, you can like tune it a little bit more and say like I don't know, if weight 1 was like 5, you're like, well, that's like really affecting the output, but we really want to make that lower because that's such a big impact. You can use this algorithm to say like, okay, like let's make it 3. And you just you do this iteratively with all the different weights. So over time, like you do this like 100 times, your weights basically like converge to what they should be. Then all of a sudden, like you put in some new data and you get like the correct answer. That's like the high level picture of backpropagation. Does that make sense?
The low level details involve lots and lots of chain rule. But oh, yeah, so this isn't just a problem modeling like functions from Rm to Rn. But you can actually model entire function classes. I won't get into it. You can look this up if you want. Any physics majors here by any chance? Let's go. Okay, there's also unsupervised learning, which I said earlier, where you're trying to learn an underlying structure behind your data. So if you're given like a bunch of pictures, for example, or like words, and you're trying to cluster them together to see like there are more negative or positive words if you're trying to do like semantic analysis over tweets or something along those lines. One of those methods involves like autoencoders where you have a reconstruction loss. I'll go into that in a little bit. So the basic idea is you're trying to summarize your data. So again, we're going to work with the data. We're going to work in the case where we have vector space data. So you have like, and for convenience, we're going to assume it's like Rn to Rn. So if you have like this huge vector, and you're trying to compress it and then like decompress it, where this is like some neural network, this is some neural network. This is called the encoder. This is called the decoder. And what you're trying to do is you're trying to minimize the distance between the input and output. So you're trying to make these encoders as robust as possible to minimize information loss. This is very similar to PCA, SVD, eigenvalue decomposition. We love math. And there are special tricks you can do to make these learned representations robust to certain types of transformations. So for example, if I'm given your photo and I rotate it, I'm still looking at the same photo. So intuitively, the representation of that photo should be the same throughout all those different transformations. And there are tricks you can do to apply this to problems in chemistry because like the configuration of the atom is invariant to SO3 or something. If you want to talk about it, we can. And there's also diffusion, which is a different type of paradigm in the unsupervised learning world, where you're given an image and basically you're trained to denoise it. So you have an image, you denoise it slightly until it's undistinguishable, and what you're training the neural network is what you're training the neural network to do is to predict a slightly denoised version of your current noisy input. And by doing this, you can sample your distribution from random noise. And that's how you get ChatGPT's image outputs or DALL-E or your diffusion flavor of choice. Okay, so in this case, we've been talking about vector spaces from Rn to Rn, but there are certain tricks you can do to optimize your performance. When you know that the input and output space is of a particular distribution. What do I mean by that? So when you're dealing with images, okay, I got ahead of myself. When you're dealing with images, you know that stuff the images embody some type of locality, right? So like have like a cat picture or something, this pixel is very related to this pixel. It's of the same object, right? Which could be very different in the case in the case where you're dealing with like vector spaces, where this element might be correlated with the one here and so on and so forth. So you can design your neural networks to have this type of locality or translation invariance, if you will, where you apply a convolution and you basically do pattern matching. And this pattern matching assumes that the things you are looking for are related to each other spatially. Here's a bunch of math. We love math. And if you're dealing with groups, the type of invariance you're dealing with is different. What you're dealing with is permutation invariances, because it doesn't, if you have like a social network, you're friends with him, he's friends with